Welcome to UV Physics Academy. So here we are discussing quantum algorithms. In this fifth part, I'm going to discuss about Deutsch-Jozsa algorithm. So what is this algorithm? So earlier in Deutsch algorithm, we have a function which is having inputs 0 and 1 and output is f of 0 and f of 1. But in this algorithm, we have n number of inputs. So that's the one difference. Okay. So here, our aim is same. That means we have to find the nature of the function. Our aim is to identify the nature of the function, whether the function is balanced or constant. Okay. So let me write this. Our aim is to find whether this f of x is balanced or constant. Okay, right. So here the only difference is we have n number of inputs. Now let me take the quantum circuit corresponding to this DJ algorithm. Right. So this is the quantum circuit corresponding to this DJ algorithm. So let us suppose here we have n number of inputs. So to indicate that, here I am taking just a notation like this. That means we have n number of parallel inputs of zeros. And on that n number of inputs, so here we have head mod gates. Here also let us take n. That means n number of head mod operators are operating parallel on these inputs, right? So here I'm taking this one. So again here head mod operation, and after this here again I'm taking the same notation. That means n number of times it is operating something like this. And after that we have measurement like this, right? So this is the quantum circuit. Now let us start. And here this is based on this phase kickback. Let me take that also. So here we have x and this is a minus. Okay, so under this operation, unitary operation, here you will get minus 1 whole power f of x and x minus 1 minus x, right? Now let me take the input. Here it is h tensor n, tensor product h operates on 0. So here I'm writing just n. That means just I'm writing that if we have n number of zeros. So tensor 1. This can be written as h tensor n operates on 0. Okay. So tensor h operates on 1. I can write this as minus. So what about this first one? I have already explained in this quantum parallelism video. So this is h tensor n operates on this 0 uh, n bit string. Okay, so this is n bit string which we have zeros, all zeros. This is nothing but 1 over root capital N summation x, but x takes values from 0 to n minus 1. So we can take this is the decimal notation, no issue, nothing will happen. And capital N is nothing but a 2 power small n, where n is the number of qubits. So just I am writing that. Then it is 1 over root n. Let me write here. So finally, we will get 1 over root n summation x, and this is x is equal to 0 to n minus 1, and after that minus state as usual. Okay, so right now after this we have uf operation. So that means so uf is operating on this. Just apply this phase kickback rule. So this is nothing but 1 over root n. Okay, so summation minus 1 whole power f of x. Just I am applying this phase kickback rule. So x minus, where x is equal to 0 to n minus 1. So we have done this oracle operation also. And after that we have this head mod operation again. Okay, so this is important. So here we have again this head mod operation. So h tensor n, but this time actually this is we can write like this also. 1 minute. This is nothing but h tensor n tensor I. So this I is on minus, okay, this one, and h tensor n is operating on this x. I hope you remember in the quantum parallelism video I have already explained this. Uh, Whenever h tensor n operates on this x, let us suppose this is a n qubit string, okay, this is a 1 over root n summation, let us suppose some z. But here we have one phase factor, that is minus 1 whole power x dot z. I have given one tabular form also, that phase factors tabular form. Okay, so this is very important. Right. So let me take it and let me take this and substitute. So then finally, once you have operated, this is a 1 over root n. So one more 1 over root n is there. That's why whole square. Okay, so here remember this is a summation over z, because uh, we are writing this linear combination of z. Z is equal to 0 to n minus 1. Now I'm just taking this and substituting here in the place of h tensor n operating on x. So then this can be written as summation over z. Okay, so z is equal to 0 to n minus 1, and finally here I am writing this z and the rest of the thing. So please observe carefully. So in the middle I have this is summation x is equal to 0 to n minus 1 minus 1 whole power f of x. Okay, so into minus 1 whole power x dot z. I hope now you understand. Just take this and substitute, nothing else. Okay, so that's it. This can be written as 1 by n summation z is equal to 0 to n minus 1, and this is summation x equal to 0 to n minus 1 minus 1 whole power f of x minus 1 whole power x dot z uh, into z. That's it. Okay, so after operating this head mod operator here, this one, so finally we got this result. Now the measurement. So here in this algorithm we are checking whether we are getting the output 0 or not. That means just I'm checking whether z is equal to 0 or not. If I get probability of finding or probability of getting z equal to 0 is 1, then definitely I will get the output is 0. If it is not, I mean, we won't get that 0 output. So in this algorithm, we are checking whether the output value is a 0 or not by using that condition, whether f of x is balanced or f of x is a constant. So let me take this last step again. So please wait. Here I forgot to take here minus, and this minus state is as usual. So here we will get this minus state because h operates on 1. Sorry, h operates on 1. You will get this diagonal basis, that is minus. So let me take that last step again. Now here, this is what I am saying. Uh, we are checking the nature of the f of x by assuming the output is 0. That means whether the output is a 0 or not, that is what we are checking. Okay, fine. So output here, once you make a measurement, okay, now I am assuming let z is equal to 0. Of course, n qubit string 0. So if z is equal to 0, this minus 1 whole power x dot z. So definitely x dot z, this is always equal to plus 1 because a whole power 0. So then forget about this. We left with, I'm taking the amplitude now, amplitude of uh, z, that is we have already taken as 0. So this is nothing but 1 by n summation minus 1 whole power f of x. Normalization factor also I have taken. That's it, because the minus 1 whole power x dot z become 1. Fine. So this is x is equal to 0 to n minus 1. Okay, right. Now here, now I am assuming f of x is a constant or f of x is a balanced. Now let us suppose f of x is a constant. So what is the meaning of f of x is a constant? For all x inputs, its value is some constant c. Let us suppose that f of x is equal to c. That c may be a 0 or a 1. I hope you know that. So then it is 1 by n summation minus 1 whole power c, but this c can be either 0 or 1. Okay. So fine, but this is the summation from 0 to n minus 1. So total n numbers are there. That's why it will be 1 over n. If it is a 0, c is equal to 0, you will get a plus n. If it c equal to 1, you will get a minus n. That's why it is a plus or minus n. So you will get plus or minus 1. Then if I find the probability of getting the measurement 0. Here if I find the probability, I am getting a 1. So this is a possible when f of x is a constant. So if f of x is a not constant, or if f of x is a balanced, then you should not get that output 0. Okay. So let us check. Now I am assuming f of x is a balanced. So what is the meaning of f of x is balanced? Means half of the inputs, half of the f of x values takes 0 value, half of remaining half will take a 1. So you can take this. That means here once again I am taking the amplitude, that is a 1 over n summation minus 1 whole power f of x. So here what I am taking is half of the values, half of f of x takes 0, and remaining half of f of x takes 1. Then this summation can be written as now half 1 by n summation minus 1 whole power f of 0, okay, plus 1 by 2 1 by n summation minus 1 whole power f of 1, let us suppose. Then here f of 0 equal to 0. So definitely here you will get a plus 1, and here f of 1 equal to 1. That's why here you will get a minus 1. So finally here you will get a 0. Okay. So finally if f of x is a balance, then the probability of finding or probability of getting output, probability of getting a measured output is a 0, is nothing but a 0. So if f of x is balanced, we are sure that we won't get that output as a 0. If f of x is a constant, then only we'll get the probability of getting output 0 as a 1. So we'll get the output 0 if f of x is constant. So this is Jozsa algorithm. So in which we are checking or we are finding the nature of f of x, whether it is a constant or balanced. But here the difference between Deutsch algorithm and DJ algorithm is in this case f of x is having n number of inputs, and earlier algorithm we have 2 inputs. Okay, right? Right. So earlier we have already explained this a DJ algorithm, Jozsa algorithm. Now here I am taking one example, but here I am explaining this example by using a decimal state notation. So I hope you already know what is this decimal state notation. Now here this is the circuit. I have taken 2 qubits. Earlier in our discussion we have taken here n number of qubits. But here for example I have taken this 2 number of qubits. Okay, fine. So what is this initial state? Here we have 0 0 1. On that our these 3 head-mod gates are operating. That means this H tensor 3 operating on 0 0 1. Now first let us take the sign phase factors. So the last one here we have 1. So you have to start with plus minus, next 0, repeat as it is, next again 0, repeat the earlier things as it is, plus minus plus minus. Now since 3 qubits are there, that's why it is a 1 over root 8. So this is a 0, minus 1, plus 2, minus 3, plus 4, minus 5, plus 6, and minus 7. Right. So now we have to operate this oracle function here, that is UF. So how to construct this oracle? So now here I'm considering construction of oracle. So earlier we have already discussed, if the function is constant, no need to do anything, just proceed as it is. But here I am assuming the function, given function f of x is balanced. So let us suppose f of x is balanced. Then how to construct the oracle? So here this oracle operation is given by, here we have 2 qubits and here one more. So this is nothing but, 1 minute. Right. So here from first qubit to here, one C naught, and the second qubit to here, one more Q naught. Sorry, C naught. Now from this we can write a decimal state notation 1 2 4. Okay, so this is the first one, x 4 to 1, that's why 4 comma 5, and you have to add the remaining, that is x of 6 comma 7. Okay, so next C naught is from 2 to 3 and you have to add 4, that's why this become 6 comma 7. So here we have 6 comma 7, 6 comma 7, two things side by side, so you can cancel because it is identity. So how to write this unitary operator? Here in this decimal state notation, writing that unitary operator is also very easy. So here 2 and 3 are interchanging or flip, and 4 and 5 flip. So that's why you can write this unitary operator. The corresponding unitary operator is nothing but, so I'm writing like this, D for diagonal. Okay, so 0 1 no flip, that's why I, 2 3 flip is there, that's why X, and 4 5 is flipping, that's why X, and 6 7 no, that's why I. So the diagonal I X X I. So if you want you can write that unitary matrix here. So what I'm saying is, here this is, so here we can write this as I, X, and again X and I. So this is 0 1 2 3 4 5 6 7. So no need to get confusion, 0 1 2 3 like that you have to write. Okay, fine. So this is a 0 and here also 0. Okay, fine. Now let us apply this unitary operator, that is this oracle. So if you operate that, 4 become 5, 5 to 4, and 2 to 3, 3 to 4. So this, after this operation of this oracle, 1 over root 8, this is 0 as it is, 1, and 2 become 3, and 3 become minus 2, I mean 3 to 2, and next 4 to 5, and 5 to 4, 6 and 7 as it is. Okay, right. Now we are going to operate this head mod operation. So if you observe carefully, the two head mods are there. Okay, so let me explain this head mod operation by using this decimal state notation. This is also very easy, no need to get confusion. So here we have two head marks. Okay, actually we have three qubits, 1, 2, 3. So this is 1, 2, 4, but head mod operators are here and here. So then you have to take the first head mod gate. Let us suppose the fourth one here. This is a h of 0 comma 4, and you have to add the remaining, that is a h of 1 comma 5, and again you have to add 2 because the 2 remains, 2 comma 6, and h of 3 comma 7. Next again you have to take the second one, that is h of 0 comma 2, and you have to add 1, 1 comma 3. Next 4 remains, you have to add 4, 4 comma 6, and 5 comma 7. That's it. So let me take the next slide. Right, so here we have actually three head mod operator, I'm sorry, two head mod operators. So this is nothing but a h, a tensor h, tensor I. So identity, no need to write the operation. So let us start. Now here we have a 0 comma 4. So carefully observe, 1 over root 8. Let me write 0 minus 1 minus 2. I'm writing in the order, plus 3 minus 4 plus 5 plus 6 and minus 7. Now you have to go in the order, right? I have already explained this method. You have to go from left to right. Okay. So this is a first I have to operate these head mod operations. That is a 0 comma 4. So here we have 0, 0 minus 4. Just cancel and write 4 because it is on. The first one is off, second one is on. First one is off, second one is on. If it is off, plus you will get. If it is on, you will get minus. So if any confusion, I request you please watch that video, how to solve any quantum circuit using a new approach, a new method. Next one, I have 1 and 5 combination, but I am taking minus common, then 1 minus 5. So 1 minus 5 is nothing but 5. Cancel this 1 and 5. Next 2, 6 combination, minus taken common, 2 minus 6. So minus 6 means 6. 2 minus 6 is 6. Next 3 and 7 combination, you have 3 minus 7. No need to take minus common, plus, but here minus is there, that's why on, which is on here, 7. Now no need to write any decimal state notation, leave it. So one head mod operation is over. And the next one more head mod operation is there. Okay, so with this, the second one here. So let us proceed. Here first one is 0 comma 2, no, nothing. Next 1 comma 3, no. But here we have 4 comma 6, cancel 4 and 6, but it is a 4 minus a 6, that's why you can write it as 6. Next minus common, 5 minus a 7, so that's why on, so which is on here 7. Minus 6 minus 7. So only 2 states remain, that's why finally I will write 1 over root. Now I am converting into binary. So this is nothing but 1 over root 2, 1 1 0 minus 1 1 1. Now I can take common. This is first 2 qubits are common. Then after that 1 over root 2, 0 minus 1. This is 0 minus 1 is nothing but this diagonal basis minus 1 1, and this is minus 8. Now once you make a measurement here, so now already you came here, that means 1 1, this is minus as it is. Once you make a measurement here, you will get 1 1 minus. That's it. First 2 qubits are measured to be 1 1. So if you once you make the measurement here, if you get 1 1, then you will confirm that the function is balanced. So this is the oracle. Now let me explain one more example by taking a 3 qubits there. That means 3 zeros there. Let us check. Actually, I forgot to explain one more thing. So what I have observed is, for example, if you have 3 head mod gates in this circuit, so this is a quite interesting one. So if you observe carefully, here we have 3 head mod gates. So this is my observation. I don't know whether this is valid for all the circuits or not. That means for all the circuits means a 3 number, 4 number of inputs, something like that. Okay, what I have observed is, here we have 3 inputs, that is 0, 0, 1. So 3 head mod operations are there. So I hope you remember this table. So here we have 0, 0, 1, this one. Okay, if you observe carefully, 0, 0, 1. I always take that bottom one as LSB. So for this, what are the sign conventions? First one is 1, that's why plus minus. Next 0 repeated, plus minus. Again 0 repeated, plus minus. Now what I'm saying is, if f of x is balanced, if f of x is balanced, okay, so after operating this UF, that means after operating this oracle function, I mean UF, unitary operator, then we are getting this last one. So the last one, that is a triple one, here we have plus minus, and 1 came, minus plus, you have to multiply with the minus extra, and again minus came, sorry, 1 came, that's why minus, plus, plus, minus. Let me write in the order one more time. So here first one is plus, sorry, 1, plus, minus, again 1, minus, plus, again 1, minus, plus, plus, minus. Like this. So after operating this, I mean this oracle function, that is we have already discussed this, 3 qubits we have. So this is C0 and here one more C0. Then we are getting this. Now carefully observe, this is the answer we got. That means 1 over root 8, linear combination of these 8 states, which is nothing but, I can write this as H tensor 3 1 1 1, right? So that means after operating this oracle here, so I'm getting this one. This is nothing but the last row. So that is nothing but H tensor 3. That is H tensor 3 operating on triple one. Now I am separating the first two, that is H tensor 2 1 1 and H1. This H1 is nothing but minus. So here we got H tensor 2 1 1. Now I'm coming back to the head mod operation, these two. I hope you are observing. Okay, so I have to operate 2 head mod operators on the first 2 qubits. Then again, if I operate this head mod operations on these first 2 qubits, then definitely this is nothing but H1 tensor H1 minus. Now I am operating again the 2 head mod operators, that is H square 1 tensor H square 1, and this is a minus as it is. So this is identity. So again you will get 1 1 minus. So this is what I have observed in this algorithm. That means from this table we are what I observed is, if f of x is balanced, we are getting this last one. After that unitary operation, so we are getting this last one. That last one is nothing but H tensor 3 triple 1. So just split it, H tensor 2 double 1 and H1. That H operates on 1 is nothing but a minus state, diagonal basis, and the remaining H tensor 2 as it is. Now On that, again you are operating two head mod operations here. So that's why again it become identity. So finally we are getting a 1 1. Like this also, by using this phase table, and this is a two ways we are using this table. One is a phase factors, another one is a head mod operations. Okay, right. So I hope you understand this. Right. So let us take one more example for this DJ algorithm, Deutsch Jozsa algorithm. So here I have taken 4 qubits. So this is the initial state. H tensor 4 operates on 0, 0, 0, 1. Now here we have starting one is 1. So that's why the phase factors starts with the plus minus. And after that all zeros are there. That's why it will be repeated as it is. Plus minus again, again plus minus, plus minus. Like this alternate plus minus, alternate plus minus you will get. 0 to 15. 0 to 15. So if I write 1 over root 16, this will be a 0, minus 1, alternate plus minus, plus 2, minus 3, plus 4, minus 5, plus 6, minus 7, plus 8, minus 9, plus 10, 1 minute, minus 11, plus 12, minus 13, plus 14, minus 15, somewhere, fine. So that's it. Okay, now you have to operate this unitary operator, that is UF, but it depends upon the function nature. Now I am assuming let f of x is balanced. So you get a doubt. You are writing only the oracle for f of x is if f of x is balanced. What about if f of x is a constant? If f of x is constant, no need to do anything, simply identity operator. So directly operate this head mod operators 3, and here it is identity on this state. Okay, again you will get back to 0, 0, 0, 1. Okay, so that's it. Now so now I have taken this f of x is a balance. Then what about this oracle? So the construction of oracle, this is quite interesting. I mean, in this decimal algebra, it is easy to get that unitary matrix. So I'm not saying this is the only the right method. So I feel this is a little bit easy. That's why I'm sharing all these ideas with you. Okay. So here we have the oracle. So 4 qubits states. So then I have to take a 1, 2, 4, 8 decimal state notation. So the oracle is constructed like this. Next C naught is from 4. Next C naught is from 2. Right? Then here we have to write this C naught operations. X, first one is 8 comma 9. And next you have to add the remaining 2, 10 comma 11. Next you have to add 4, that is 12 comma 13, and x 14 comma 15. So this method I have already explained earlier, so I request you please go through that. And the next gate is a 4 comma 5, that means 4 to 1, 4 comma 5. You have to add the remaining, that is a 6 comma 7, I have added 2. Next you have to add 8, that is a 12 comma 13, and a 14 comma 15. But I don't know whether this is the proper way or not, but we are getting the result finally. That is what I have observed. And the next C naught, that is a 2 comma 3. So you have to add 4, that is 6 comma 7, and next you have to add 8, that is a 10 comma 11, and this is a 14 comma 15. So if any two same operators side by side, you can cancel that. That is nothing but identity. So here I am cancelling this 6 7 6 7, and 12 13 12 13, and 10 11 10 11. You will get a doubt. 10 11 operations are not side by side. How you cancel? Actually, in the middle, if you observe carefully, there is no 10 and 11 number. So this is the advantage of getting unitary operator very easily with this decimal state notation. So you can commute. I mean, these things will commute with each other because here there is no 10 and 11. So that's why you can apply that commutation law. So that a 10 comma 11 will come this side and it will be cancelled because x into x I. But remember, numbers must be same. Whenever you are multiplying x 6 comma 7 into x 6 comma 7, then only it will become I 6 comma 7, right? And 14 15 14 15 cancel, but still one more 14 15 left. So now see how I am going to write this unitary operator very easily. So D for diagonal. Okay, I am writing the diagonal matrices elements. So this is a 0 1. No, here no operation of a 0 1 involving with this x. So that's why identity. Next 2 3, yes, here it is, that's why x. 4 5, here it is, that's why x. 6 7, no, it's cancelled actually, that's why I. 8 9, it is x. 10 11, no, identity. 12 13, no, that's why identity. 14 15, yes, it is there, that's why it is x. So then you will get that unitary operator. Okay, so once you operate this unitary operator on this initial state, okay, initial state means after this head mod operations, it will flip 2 to 3 and 3 to 2, 4 to 5, 4 and 5, 8 and 9 and 14 and 15. Then this is nothing but 1 over root 16, 0 as it is, 1 as it is, and a 2 and a 3 flip. That's why I'm writing minus 2. I hope now you understand what I'm writing. So this 2 is going here and 3 will come here. So that's why I'm writing directly minus 2 plus 3. Next 4 5 flip. So that's why minus 4, careful, plus 5. Next 6 7, no change. Next 8 9, yes, flip, minus 8 plus 9. Next 10 11, no change. Next 12 13, no change. 14 15 flip, minus 14 and plus 15. After this you have to apply head mod operations. So the head mod operations, here we have 3 head mod operations. Okay, you have to be very careful. So here 3 head mod operations are there. So this is H, single qubit quantum gate, and here also H, and this is I. But instead of operating this, what I observed is, if you draw this table, okay, so if you draw this table, our technique is there. So what I said earlier, we are getting the last one. Let me check. So here I am not operating this head mod operations. Okay, so I have already explained how to operate. If you are interested, just check that also. 1 2 4 8, and you know how to write the operations and how to cancel the states. You please check. But here I am taking another method. Check carefully. So what I observed is, if f of x is balanced, we are getting this last one in this table. So the last one is what? All ones. So that's why just I am checking. So what is this? H tensor 4 triple 1. Sorry, 4 ones. Now careful. Here starting one is 1, last LSB. So plus, minus, again 1, minus, plus, again 1. Whenever 1 came, you have to multiply with minus extra. Minus, careful, plus, plus, minus. Again 1 came, so that's why minus, plus, plus, minus, plus, minus, minus, plus. Now please check. So this entire thing is nothing but this one. Same. So what I'm saying is you can write this entire thing is nothing but h tensor 4 4 ones. Then what I will do, I will split it h tensor 3 triple 1 h1. Then h1 is nothing but minus, and finally here we get h tensor 3, right? And after that again you have three head mod operations. So that head mod 3 operations, and here 3 head mod operations will give you identity, and finally you get this triple 1 and minus. Once you make a measurement here, you will get 1. So this is very easy to understand with this table. This is also very crucial. Okay, so in two ways we are using this table: phase factors we are using, and as well as this head mod operations. And what I observed is, if f of x is balanced, we are always getting this last one. I have verified up to 4 and 5 qubits also I have verified. Okay, so you please also check if any correction is there in my explanation, so please let me know. Okay, so I don't know still whether this is valid method or not, but still we are getting the results. So whatever we are getting this unitary operator exactly matching with the matrix multiplication also. Okay, so right, thank you. I hope you understand this algorithm examples. I have explained two examples. This is 3 qubits and as well as 4 qubits. So I have explained how to write this unitary operator corresponding to that oracle when f of x is balanced. And remember, if f of x is a constant, you need not to do anything, simply identity operations, and you will get the same state again. Okay, so thank you, and we'll meet again in the next video.